Okay, so we have question 4 from the Step 2 2024 paper, and this question is about vectors. So as always, if you want to try the question, this is the full question here, but I'll get into the first part. So they start off by giving us a definition of what a bisecting vector is. It basically needs to just satisfy these conditions, and then they give us a scenario. So we have basically the same situation as they give in the example, like three non-collinear points in three-dimensional space. And then they define B to be this vector. And then they want us to show that B is a bisecting vector for the angle x or y. So you can start off by drawing a diagram if you want, but you don't really need to do that for this first part because you just try and show that, or show the definition that they give, right? So we need to try and prove that the angle between x and b is equal to the angle between x and y, and that both of those angles are less than 90 degrees. And you can do that all with just the dot product. So if we try and calculate the dot product between the two vectors, or try and find the dot product between x and y, and or no, x and b and y and b, to find the two angles, our goal is basically to just show that these angles are the same, right? So let's first try and simplify cos theta 1. So cos theta 1 is, after we substitute b at least, is equal to this. And then if you know the properties of dot product, which you probably should know if you're picking a vectors question in STEP, you can basically distribute out the x. And by definition, a vector dotted with itself is just the vector squared, or its magnitude squared. So you get something like this, and then you can basically cancel out the x, right? So the magnitude of x in this term and the magnitude of x in this term divided by magnitude of x, and you get something like this. And then you can do something similar for the other angle, but in this case you just cancel out the y's, and you get something like this, which is equal to each other, right? Because the dot product is, I don't know what the word is, but y dotted with x is the same as x dotted with y. Anyway, now we need to show that both of the angles are less than 90 degrees, right? Well, we know they're the same angle, so we just need to show that one of them is less than 90 degrees. Oh yeah, also I should mention, they're the same angle because they have the same cosine, right? So yeah, if that wasn't clear enough. So to show that they're less than 90 degrees, we need to show that cos of theta is greater than 0, right? Because if you consider the cosine graph between 0 and 180 degrees, when it's less than 90 degrees, the cosine is positive, right? So it's above the x-axis, so it's greater than 0. So we need to basically show that this numerator is greater than 0. And to do that, we can consider the dot product, right? Because we can get an inequality from that. And that involves like these two terms. Just consider when, so just consider when cos theta is -1 and cos theta is 1 to get the full range. And then you get something like this, right? But the problem is, if we use this, we'll be able to say that cos theta is greater than or equal to 0, right? Or, I mean, cos theta 1 is greater than or equal to 0. But we want that cos theta 1 is greater than 0, right? Like a strict inequality. So in order to do that, we need to somehow remove this this strictness. I mean, we need to make this strict somehow, right? So we need to say, okay, can cos theta ever equal -1 or 1, right? The only cases where it's ever equal is if x and y are the same vector, right? But we know that x and y are not the same vector because they're non-collinear points, right? So that basically, that causes the strictness, right? So we know that cos theta is between this minus 1 and 1. And from there, we can say that, okay, from there we can say that this inequality holds. So yeah, these cosines are greater than 0, which means both the angles are less than 90. So B is a bisecting vector. The next part is they want us to explain why, or explain using a diagram, why any other bisecting vector for angle x or y is a positive multiple of B. So I drew this diagram, right? If you imagine this vector, vector x, and then this vector y, B is basically when you add the two vectors, magnitude y times x plus magnitude x times y, and it forms basically sort of a parallelogram, I guess. Yeah, so any other bisecting vector has to lie on this line, which is the vector line B, right? Which means that if it lies on this line, it needs to be a multiple of B. Anyway, for part B and part C, part B, they want us to find the value lambda such that the point B, defined by OB is equal to lambda B, lies on the line XY. Okay, so they basically want us to find this lambda, where if we imagine scaling the vector B, that vector will land on the line XY. Okay, so this is very similar to like the GCSE type questions where you basically need to find two paths to a point and then compare coefficients. So what we can say is we can introduce a new scalar as well. If we say that, okay, well, we can just go lambda b, or we can go, what I mean is we can just go lambda b to get to that point there, or we can go x plus some scalar multiple of the vector xy. And those will get to the same point, right? And then we can set those two vectors equal to each other. And when we do this, we can compare coefficients, right? Because we know b is in terms of x and y, so we just compare the x and y vectors. So to compare them, we just substitute the definition of b, which was in terms of x and y, and then set the y vectors equal to the y vectors on the other side, and do the same with the x vectors, right? So when you do that, you'll get these equations, and it's a simultaneous equation, right, in terms of two variables, so you can solve for each of them. So when you solve for lambda, you get this, and then mu is equal to this, right? And going back to what they wanted lambda, so we found that. And they also want the ratio in which point B divides xy. Well, we said that to get to B from x, you had to go mu amounts of xy, right? So this amounts of xy. So you can think of it like this. If we had to go mu amounts to get to B, that means that to get from B to Y, that has to be 1 minus mu, right? Which is just going to be y over x plus y. So basically B divides xy in the ratio x to y. So the ratio is x to y. The magnitude of x and y specifically. For part C, they ask us to show in the case when OB is perpendicular to xy, that the triangle XOY is isosceles. So the first idea could be to show that two sides of this triangle are equal. So yeah, we can use the fact that OB is perpendicular to XY, which means that the dot product between OB is the dot product between the vector OB and the vector XY is equal to 0, right? Because they're perpendicular, so the angle is 90 degrees. And when you do that, you get, or you should get an equation like this. And then you just need to distribute, right? When you do that, you'll get something like this. And it looks a bit tricky to go from here, but we know we need to factorize this, right? And we also notice that there's a little bit of symmetry in this equation. So if you group them up like these, right, where we factorize out y in these terms, and then we factorize out x in this term, you'll get this, and the inside of these two are the same, right? So you can just factorize out this to get something like this. So either this is equal to 0 or this is equal to 0. But we know that from before, right? We know from before that the only case where this is ever equals 0 is if x and y are the same vectors. But we know they're not because they're non-collinear. So the only other case is if y is equal to x, which means that the triangle is isosceles. So the last part is honestly the trickiest part of this whole question. They give us 4 points, and yeah, it's in 3-dimensional space, so you can sort of imagine it as like a tetrahedron. And then they define a bisecting vector for these 3 angles, and then they want us to show that the 3 angles between them are either all acute, all obtuse, or all right angles. So they're referring to the angles between the bisecting vectors, right? So let's just start off by like defining or like setting up some variables for some of these things. Let's let the bisecting vectors of these 3 angles be u, v, and w, and then the position vectors of p, q, and r be p, q, and r. So using the first part of this question, we know that if we basically have a have uh, how can I describe this? If we basically have a triangle in 3-dimensional space and they're non-collinear, we can define the bisecting vector to be in terms of those 2 vectors. So in here, we just use that idea to define u, v, and w in terms of p, q, and r, right? Because you can just imagine, like these individual bisecting vectors to just be like consider those to be like a similar case to what we did in the first part. So if we remember, if an angle is acute, that means that the cosine has to be greater than 0, right? If it's obtuse, the cosine is less than 0, and if it's a right angle, then the cosine is equal to 0. So let's just start by finding out one of the angles. So I pick u and v to find the angle between them. So when we sub in the values of u and v into what we have here, we get this, and then we need to expand it out, which gives us something like this, right? And sort of a common theme in this question is about the symmetry of these vectors. If you can think about, if you look at these 3 vectors, right, there's sort of some symmetry between them in the fact that they choose 2 of these 3 vectors, right, and then it's like a combination between them. For this cosine, if we factorize out the magnitude of q from it, we get something like this. And this is symmetrical in this term, right? Yeah, so if it's symmetrical in this term, that means that it doesn't matter whether or not you started off with uh, P, Q, or R, you'll eventually get this term, right? So imagine we did V and W instead. We'll eventually get this term, right? Because this term is symmetrical, so we can basically interchange, or we can basically swap Q with P, P with R, or swap any combination of these, right? And this will always stay the same. So the angle between this vector and this vector will have this term. The angle between this vector and this vector will have this term as well. So the angle between all three of those bisecting vectors, UV, VW, and then UW, those three angles will always have this term. And in fact, this term is actually what determines whether or not the cosine function is positive, negative, or equal to 0, right? Because we know that this magnitude has to be greater than 0, and then obviously the denominator is greater than 0, right? And that's going to be true for all the other dot products, right? So the only thing that would really change is this and this, but that doesn't really matter because those are magnitudes, so they're always positive. So this is the thing that determines the sign. So from that we can conclude, well, if this term determines the sign, whether or not it's positive, negative, or 0, then and we know that this term is going to appear in all three of the dot products. That means that all three of the angles are going to have the same sign, right? If any if this is greater than 0, then all of the dot products are going to be greater than 0, right? If this is 0, then all of the other ones are going to be 0. If this is less than 0, then all of the other ones are going to be less than 0, right? So that means that all three angles will either be acute, right angled, or all obtuse. They should say obtuse somewhere. So yeah, that is kind of tricky to figure out, but once you know, like, that's the trick, then it's not too bad.